In this video, I'm going to teach lesson 6.4c for IB Math SL, which is introduction to the trig identities that we might use to solve trig equations. Identities are just statements of equality. We've seen many of them in math before, though maybe haven't called them that. And there are a few that we use in SL math, and there are many, many other trig identities that we're not required to know. So I just want to show you in the formula booklet what they look like. So here's one identity. It's the identity for tangent. It's the statement that tangent theta equals sine theta over cosine theta. We use it in solving equations. If we have a tangent and we don't want to have a tangent there anymore, we could replace it with sine over cosine. And you'll see examples of this later on. We have this Pythagorean identity. I'll show you where it comes from. And then we have these two double angle formulas or double angle identities. And that's it. That's the extent of the identities that we're going to need to know and use. And in fact, we don't need to memorize them. We just need to know that they're here so we can go look them up when we need them. And you'll see throughout some examples in this lesson and the next how we use them. So first, let's unpack that tangent identity. So that's the identity that tan theta equals sine theta over cosine theta. And that theta is just an unknown angle, so often when we're solving equations, it's actually x. So that would mean you can replace tan x with sine x over cosine x. This is just another way of saying exactly the same thing. And again, you would use it if you had, let's say, a tangent in the equation and you didn't want to have that tangent. I'm going to write a possible example, though you wouldn't actually get an example like this on the test. But if you had something like this and you were attempting to solve it, you're seeing you have a cosine, you have a tangent, and you're thinking, if I don't have a calculator, I'm not going to be able to get these two things together. But you could change tangent to sine x over cosine x. So anytime you want, you can replace tan with sine x over cosine x because of the identity, because of the fact that they are equal, and they are always equal. And then you can see if that helps you get any closer to an answer. In this case, it would at least let us simplify and combine these two things together into a single fraction, which still doesn't help us much in this problem, but I did just make it up on the spot, so you don't need to worry about finishing that example. I just wanted you to see what that kind of substitution could look like. Cofunction identities for sine and cosine. These aren't really used in IB. They are common on the SAT. And the concept behind them we have talked about in IB, like when we did triangles, when we did waves. So what they are is the fact that the sine x is equal to the cosine of 90 minus x, that same angle minus x. 90 minus that same angle. And cosine x equals sine of 90 minus that same angle x. It all comes from sine and cosine in the triangle sense, which is that if x was an angle here, the sine of it would be opposite over hypotenuse, right? So I could write the equation sine x equals opposite over hypotenuse. Well, if you think about what 90 minus x means, that's going to be the other angle. Let's call it z here. That's going to be the other angle in this triangle because 90 minus x is going to be that other angle. And if you're thinking about that z, or that 90 minus x, its cosine would also be O over h because cosine is adjacent over hypotenuse. So it makes sense to say, no matter what the angle is, that the sine of x is going to equal the cosine of 90 minus x. So it all comes back to those right triangles where we first learned it. And we would have also seen them when we were translating functions. If you want to change a sine function into a cosine function, you just need to shift it over by 90. Or by pi over 2 pi. The Pythagorean identity, it says identities up there, but there's really just one. The Pythagorean identity for sine and cosine is sine squared theta plus cosine squared theta equals 1. Or you might see that as sine squared x plus cosine squared x equals 1. And we can use this in a few different rearrangements. So let's say you had a sine squared x, but you wanted it to be in terms of cosine instead. You might isolate the sine by subtracting the cosine squared from both sides of the identity. Right, so I just took this and I rearranged it over here. So you could use this substitution if you wanted to. Replace sine squared x with 1 minus cosine squared x in parentheses. And that's a valid use of the Pythagorean identity. Or perhaps you wanted to replace a cosine squared and change it to something in terms of sine. Well, you could use this version of the identity instead. So this one we can use in a couple of rearranged ways. This all comes from, just so you understand the concept, the idea that if you have a point on the coordinate plane, you might call it xy, let's say, and if we had this distance there from the origin to the point xy, you could imagine a right triangle. I'm going to use theta for the angle instead of x because I've already used x to represent that variable x and y. Then this side would be x and this side would be y. If I asked you to talk about, let's say that the hypotenuse is 1. So if I asked you to talk about the sine of this theta, you might say the sine of theta equals y over 1. Well, y over 1 is just y. So sine theta equals y if the hypotenuse is 1. So I could just label this y, erase it, and change it to sine theta. And then similarly, if I was talking about the cosine of theta, you could say it's x over 1 because it's adjacent over hypotenuse, which is just x. So cosine theta is x. I can take away that x, erase it, and change it to a cosine theta. And now because of the Pythagorean theorem, I could write the true statement that sine squared theta plus cosine squared theta equals 1. And that's where the Pythagorean identity comes from. Even if the hypotenuse was not 1, the sine theta could always be labeled here because it's always going to reduce to that same ratio. So that's where the Pythagorean identity comes from. We have an example now. Yay! Express 2 cosine squared x plus sine x in terms of sine only. Okay. So the original expression given, this is for part A, is 2 cosine squared x plus sine x. We want it to be in terms of sine only. This part already is in terms of sine, so it's really just this that we need to worry about. We can consult our formula booklet, if you can't remember, as far back as this identity. We know that sine squared x plus cosine squared x equals 1, and therefore if I'm trying to replace a cosine squared, I want to use the rearranged version of this formula that looks like this. And so I'll come over here to where I have a cosine squared, open up a set of parentheses, and in those parentheses I'm going to replace cosine squared theta with its equivalent expression from the identity, 1 minus sine squared theta. And then I will clean it up and simplify a little bit. Distributing the 2 through those parentheses, that was the 2 from the original expression there. And I'm going to rearrange this thing to make it look like a standard form quadratic, because I sense what's coming next in the next part of this question. So I just rearranged it. I kept the quadratic term first, then the regular sine x term, and then I moved that positive 2 to the end. So this would be my most simplified version of the answer to A, though I actually could have stopped here. This was in terms of sine only. And now it asks me to solve the equation 2 cosine squared x plus sine x equals negative 1. So this is the same expression from part A, and now I have a new version of it that's all in terms of sine. So that's the version I'm going to use. It's going to be easier for me to deal with. And it's telling me to set it equal to negative 1 and try to solve it. So for part B, I'm going to take my sine version of the expression, set it equal to negative 1, and then look and see if I can solve either with or, oh, I can't solve it with the calculator because it says express your answers exactly. So I'm going to attempt to do this without a calculator. Exact would be something like pi over 3, not 57.9. So I'm going to add the 1 to make this thing equal 0 because I can see that it's a disguised quadratic, and it's good when quadratics equal 0. Then you can use factoring. So I forgot to add 1 to that. So adding 1 to that 2 gives us a 3 right there. If you like to use u substitution for your disguised quadratics, this is going to be rewritten as u squared plus u plus 3. So I took sine x, assigned it to the variable u, and then I've replaced all my sine x's with the letter u. This is a factorable expression. It should be if I'm attempting to do this without a calculator. They give us only factorable expressions with a negative 2u in one of the parentheses and a u in the other. And then I'm looking for something that multiplies to make a positive 3. So maybe I would choose to put a plus 1 here and a plus 3 here. And then I'm going to look at the expression, FOIL it back together, see if it gives me that quadratic, which indeed this one does. It checks out. What I'm checking for is to see if it gives us that middle term value, which is a 1u, and it does. So these are my two factors, and I can replace the u back with sine x at any point now that I've done the complicated algebra. And I'm going to set each of these factors equal to 0. and then see about solving this thing. So this is where the trig is going to come into play. So sine x equals, I'm going to subtract 3, divide by negative 2, and that's going to be 3/2. And over here, sine x is going to equal negative 1. It seems like we have a lot of work left ahead of us, but this, no solution. You cannot have a sine that is greater than 1. So sometimes this will happen when you're doing a quadratic. One of the factors just leads to no solution. That's great, less work for you. And then sine x equals negative 1, that is recognizable. We can do it without a calculator. We need to think about our unit circle and where the sine is negative 1. Sine is a y value on our unit circle. So only here is the y value negative 1, which is a 3 pi over 2 as the angle. And then I do just want to check the interval that was given in the original question, way back up at the top, to make sure I have given an answer on the correct interval. Oops, I scrolled back the slide. Indeed, it says 0 to 2 pi, and so the only solution on the interval 0 to 2 pi is going to be 3 pi over 2. So a lot of work just to get that one little answer. All right, then we get into the double angle identities for sine and cosine. So the sine double angle, so this looks like sine 2 theta in the book. That means to double your angle. So if you were talking about theta being 30 degrees, this is talking about the sine of 60 degrees. So obviously if you knew the angle theta, you could just double it and then do the sine of that new angle. But more often, they ask us about double angles when we don't know what theta is. So if we knew, for example, that the sine of theta, some angle theta, was 4/5, and we don't know what theta is, we can at least imagine that there's some triangle that has a 4 and a 5 and a theta here, because a sine is opposite over hypotenuse. We might be able to find the other side and be able to talk about like what the cosine is or the tangent is, but without a calculator, I'm never going to know what that theta is. So they're going to ask us to do something like sine 2 theta without a calculator. And it does not mean that we should just double this, because that would be 2 sine theta, right? That would be 2 multiplied by 4/5. And that's not what this 2 means when it's inside next to the theta. So this would mean to double the angle, but we don't know the angle. So in a situation like this, we go to our formula booklet and we find that there's an expression equivalent to sine 2 theta. In fact, I think I have the identities printed out again. Oh, nope, we have to go back to the first slide to see them. Past it. There it is. So we have this expression that's equivalent to sine 2 theta. 2 sine theta cosine theta. We'll go back to the slide we were working on, write that down. 2 sine theta cosine theta. This is manageable because I know I can figure out sine theta from my little triangle that I drew. I can figure out cosine theta from my little triangle I can drew because both of those are single angles. And so without ever knowing theta, I could find out what the sine of double theta is. And if you picture where that is on the coordinate plane, you're not going to get very far. Because if this is theta, double it, it might be here. It might be here. It just depends on the size of theta. We don't even know. But we could now figure out the sine of 2 theta, for example, by saying 2 times 4/5 times the cosine of theta, which if I can see from my triangle that I drew is 3/5. And then we can work this out, and it's going to turn out that the sine of 2 theta in this example that I made up on the fly here is 24 over 25, which is not something we would have necessarily expected just by knowing that the sine of theta was 4/5. So this is a helpful identity. Anytime on an exam that we see a double angle like sine 2 theta, we're going to use an identity from the booklet and change it to something in terms of single angle, right? Single angle means just theta. Double angle would be if it was 2 theta. So we'll take our double angle expression and change it to a single angle. So that's the sine one. And then the cosine one is quite a bit more complicated. Actually, I think I'm going to add a new slide for that. For cosine double angle. So cosine double angle has 3 versions in the formula booklet that we can use. And it looks a little confusing when they're all written on one line. So one version is cos theta minus sine, cos squared theta minus sine squared theta. So that's one version of the cosine double angle. There's also one that's purely in terms of sine, and there's one that's purely in terms of cosine. I'm just going to show you what they look like in the booklet so you can see what I mean, in that it looks confusing when they're all written on one line. So here they are. cosine double angle equals cosine squared minus sine squared. That's one option. Or we could do this option, which is 2 cosine squared minus 1, or 1 minus 2 sine squared. So we have all these choices. Just depends on which trig you want to get rid of and which trig you want to keep. So going forward to the slide we were on, we can also say this is equal to 2 cosine squared theta minus 1, or 1 minus 2 sine squared theta. You'll never use all of them at the same time. This equivalence, this equivalence, this equivalence. You'll tend to pick one, and if that one works out for you, then you'll stick with it. If that one doesn't work out, you might erase it and go back and try using a different substitution instead. So if we're asked to write cosine 2x in terms of only sine, we'll want to use the identity that looks like this. If we're asked to write cosine 2x in terms of only cosine, then we'll want to use the one that looked like this. If we want to write sine 2x in terms of only cosine, we're going to be out of luck because the identity for sine 2x was 2 sine x cosine x, and I don't have a way of replacing a single angle sine with anything in terms of cosine unless it was squared, and here it is not. So that's just, the answer to that question is no, we cannot write it in terms of only cosine. And then using it, so here's an example of an equation you might actually be expected to solve. We have cosine 2x plus cosine x equals 0, and we're going to try to solve it without a calculator. I cannot add these together and make it cosine 3x. That's not a thing. I would have to, anytime I see a double angle on the exam, I'm going to go to the formula booklet and I'm going to find a replacement. So I know I have 3 choices for what to replace cosine 2x with. I'm going to choose the one here that's only in terms of cosine, because the other function in this equation is cosine. And it would be easier for me if everything was the same trig function, then I might have a hope of solving it. So I'm going to replace cosine 2x with 2 cosine squared x minus 1. Bring down the plus cos x and it equals 0. Now it's a quadratic, all in terms of the same trig function. And you might try u substitution if you're attempting to solve this without a calculator. It's a little bit easier to do factoring when it's in terms of u. So 2u and u, I'm looking for like a plus 1 and a minus 1. It's the only way to make negative 1. I do a quick FOIL, see if it works, and it does. And then I'm replacing my u back with cosine x, and then setting each of these equal to 0. These should be solvable without a calculator. This one is cosine x equals 1/2. That's a recognizable ratio. And this one is cosine x equals negative 1. That's the easier one to solve because there's only one place on our unit circle where the x coordinate would be negative 1. That's over here at pi. I'm just going to double check the interval and make sure that it was a 0 to 2 pi interval. It is, so that's the only solution where where the cosine of x would be negative 1. And then on this cosine x equals 1/2, I'm thinking, where is cosine positive? In this quadrant and this quadrant. And if it's adjacent over hypotenuse, like this, where the adjacent side is a length 1, then this would be root 3, which means it's across from a 60-degree or pi over 3 angle. So x must be pi over 3, or pi over 3 in the 4th quadrant, which is like 6 pi over 3 less 1, so 5 pi over 3. And those are all of the solutions to this equation. That's